Thanks, guys. So my name's Joe, and I work for Microsoft. I'm on the MSRC Vulnerabilities and Mitigations team, and I'm here today to share with you a little bit of the engineering backstory behind both Control Flow Guard and Microsoft's greater control flow integrity strategy. And one of the things I'm going to be sharing with you is a bunch of the issues that we found with CFI technology as we've gone down this road. And just full disclosure, this is going to be a no-holds-barred talk, so even though I work for Microsoft, we are going to be sharing with you everything we know about problems with CFI, including outstanding design-level issues with Control Flow Guard, and I'll also be sharing with you guys for the first time the details of how we broke Return Flow Guard and why we ended up not shipping it. But before we dive into that, I just want to give everyone a little bit of historical context for why we even went down this crazy road. So Control Flow Guard actually started being developed for Windows in about 2011, and that initial development went into 2012. And I'm sure you guys have all seen these graphs before if you've ever watched Matt Miller give a talk, but basically the problem that Microsoft had is people continue to find more and more vulnerabilities in our products, and people were also able to exploit those vulnerabilities more and more frequently. And we needed to come up with a plan to try to keep our customers safe. And there's some realities that we have to deal with. And this slide is all framed around what was going on in 2011, 2012. But we have things like the SDL, we fuzz, we do pen testing, we have static analysis tools we work on. But no matter what we do, we just can't seem to find all the bugs. People keep finding them. We've also gone and implemented a bunch of simplistic mitigations like DEP, we have ASLR, we've done hardening on our heap metadata, et cetera, et cetera. But these simple mitigations are just not proving to be robust against the really strong primitives that people are starting to get out of their bugs, especially in the web browser. And when we look at what our options are as far as trying to keep people safe, we do have limited options. For one, obviously, anything that we end up doing needs to work for the targets that get attacked the most, so Internet Explorer and Office. One of the options that we would have certainly liked to pursue at the time was doing a lot more hardcore sandboxing for Internet Explorer and Office. But the issue for us is that both of those products have lots of compatibility concerns due to their old plugin models. And so doing any sort of sandboxing ends up running up against those compat concerns. And sandboxing also has a really huge engineering cost. And at that time, we just did not have the engineering resources to pull off that effort. And then the other issue with sandboxing too is that it really only helps protect the software that you sandbox, so all the other software running on Windows doesn't get any benefit from that. And at the end of the day, any changes that we decide to make to the Windows stack end up having really big compatibility hurdles to jump through, performance hurdles, we need to remain ABI compliant, etc. So when we're looking at doing really big pushes, we need to invest very wisely, because if we end up spending years going down a path and then we end up not being performant, it's a huge waste of time for us. And that brings us to our control flow integrity strategy. So when we went and we looked at how our customers were being attacked, we can see that all remote code execution vulnerabilities that are targeting memory safety issues end up hijacking control flow. And we realized that if we can constrain control flow to what we consider to be legitimate paths, then that's going to break all exploits as they're currently written. Now, doing control flow integrity is a really huge lift, and it does have significant performance penalties and compatibility penalties. So we don't want to just go down this road of implementing it without really thinking about, do we think this is going to make a difference in the long term, or do we think this is something that will be trivially worked around? And if it's the latter, then we're not going to waste our time. Matt Miller ended up doing a talk, I think about 5 years ago, that I linked in the slide deck that kind of outlines how Microsoft thinks about different exploitation primitives. But the gist of it is that after we thought about it for a while, we decided we think that this is a worthwhile path to go down. We do think that this will make attackers' lives more difficult. And another really nice thing is that the security teams at Microsoft were actually very well positioned to implement a lot of these changes and to help drive other teams to implement the rest of them. So it seems to work out on all fronts for us. Now, this is actually a slide that I took from an internal presentation done back in 2012. And this presentation was on how Microsoft was going to solve memory safety issues. And you can see that there's really 4 tenets to our strategy here. The first piece of it is Control Flow Guard, which probably everyone's familiar with because it's been released for a few years now. The next piece is split stacks, so we need to have something to protect return addresses stored on the stack. And in today's terminology, we would probably depend on Intel CET to provide us a hardware shadow stack. The third pillar here is image load restrictions. And so this is all about making sure that even though attackers have to follow valid control flow paths, we want to make sure that they can't load code from the system that we don't want to be loaded in that process. And in today's terminology, Microsoft has a number of different things that we do to enforce this pillar. We have Code Integrity Guard, we have No Child Process, we have restrictions that prevent you loading images from network shares and images that have low mandatory labels. And then the fourth pillar is dynamic code restrictions. And this is all about making sure that an attacker cannot just go and instantiate new executable code pages, like using virtual Bialek on Windows. And in today's terminology, this would be arbitrary code guard. And when I was going back through time, looking through all of our old documents to put this presentation together, I found this quote in an internal document. It was a CFG assessment document. And it said, "Since we'll be the first major software vendor to deploy a control flow integrity solution at scale, we will have the great distinction of being the first to experience the school of hard knocks." And this turned out to be very true, and that's what we're going to be talking about now. So the school of hard knocks, or how our understanding of CFI has evolved. And one question to answer is, how did we get here? So if you go and you might be aware that Microsoft has a mitigation bypass bounty, so we will pay you money for finding ways around our exploit mitigations. And if you go and you look under Control Flow Guard, we have this massive section of things that are considered out of scope for the bounty. And so what I hope to inform you today is, how did we come to learn that all of these design level problems exist? And what do we think we can do about them? So the first thing we're going to talk about is Control Flow Guard, because that was the first pillar of that strategy that we implemented. I'm assuming that most people know how Control Flow Guard works, but just super briefly, there's a bitmap that is loaded in each process. This bitmap indicates whether any particular virtual address is a valid indirect call target or not. And prior to any indirect call or indirect jump being made, there is a check function that checks that bitmap. If the function is not marked as valid, then the process fast fails, and if it is marked as valid, then you make the indirect call. And one thing that I'll point out here is that Control Flow Guard is coarse-grained. So there is no checking to make sure that the function you're about to indirectly call expects the same number of parameters, or that the parameters are of the correct type. It's just a binary, can this function be indirectly called or not? And the way that that list is created by default is that at compile time, any function that has its address taken is marked as a valid indirect call target. Any function that is inside of a vtable will be a valid indirect call target. And any function that is a DLL export is also a valid indirect call target. Now, prior to Control Flow Guard shipping, we did lots of analysis on it, and we had a bunch of limitations that we knew about right off the bat. An obvious one is stack corruption. Control Flow Guard makes no attempt to protect the stack. We needed our split stack pillar to do that. So we already know that if someone can find the stack, we're done. There's also a number of compatibility-related issues because when you work at Microsoft, you can't ship a mitigation if it breaks all existing software. So as a result, we have certain things such as anytime a process creates a new executable code page, by default, all the virtual addresses of that code page will be marked as valid indirect call targets. Similarly, processes that support Control Flow Guard can still load DLLs that don't support Control Flow Guard. There's some issues because control flow guard is coarse-grained. You can call functions out of context and maybe get them to do slightly unexpected things. One thing we knew about right off the bat is you could call a function out of context, and that function could end up writing a stack address onto the heap for you, depending on how you called that function. So we already knew that people were going to be able to find stack addresses. We also had a class that we just called dangerous functions. And this is primarily functions like nt-continue and long jump. These are functions that take a pointer to a context record, and they use that context record to set all of the register state. So you have direct control over the instruction pointer, the stack pointer, etc. And the last category is just generally known as data corruption. And this is the idea that an attacker doesn't actually need to hijack control flow to make a program do interesting things. For example, if there was a file path to an executable that was stored on the heap, and that file path was eventually going to be passed to winexec, then an attacker could corrupt that path using a read-write primitive, and they could, end up getting you to load an executable off of a network share. Similar attacks exist for load library and a number of other functions. Now, one thing I forgot to mention is that when control flow guard was in very early development, there really was no formal threat model for it. It was really just thought of as a way to kill ROP. But prior to CFG shipping, we actually did have a more formalized threat model for it. All the decisions that we were making for control flow guard assume that the attacker has an arbitrary read-write primitive. And with that, it's kind of implied that we also assume the attacker has full knowledge of the virtual address space of the process. So we assume the attacker knows where the stacks are, we assume they know where the heaps are, where the images are, etc. Control flow guard has to be robust even if an attacker has all of that knowledge, because the mitigation is designed to be resilient against an attacker that has these sort of info leaks. So let's go and take a walk down memory lane now. Back in November of 2014 is when control flow guard, which is the first pillar of our strategy, finally ended up shipping to the world. It took quite a while to get it out. It was delayed several Windows releases, I believe, because people were scared about performance. But we ended up shipping it as an optional update. And then something that was kind of cool for us happened. We saw some 0 days in the wild in Flash, and I think it was December of 2014. And that's never good news. But one thing that was kind of neat was that we actually caught one of these 0 days because the authors didn't realize that we had shipped control flow guard as an optional update, and their exploit didn't work with control flow guard. So in the Windows crash dumps, we started seeing all of these functions failing on the CFG check function. And so, for us as a company that's building mitigations, trying to keep people safe, we thought, this is awesome. We shipped this mitigation, and 1 month later, we just caught a 0 day. We're keeping people protected. That's great. In February of 2015, so 3 months after it shipped as an optional update, we ended up shipping it as an enabled by default mitigation for everyone on Windows 8.1. The reason we didn't do that initially is really because we were scared. Control flow guard is a really big change for the operating system, and just pushing that out to hundreds of millions of people at once, it can be a little bit scary. We don't want to break everyone. But we had enough confidence in it by then, so it's enabled by default. So now that it's enabled by default, we start monitoring what people are doing. What are attackers doing to get around control flow guard? And really the first test of it was at Pwn to Own that year. Pwn to Own happens every March, and so this was 1 month after control flow guard initially shipped. And we were pretty excited to see what people would come up with. And I think ultimately the ways that people got around control flow guard all utilized known weaknesses. We knew that this stuff could happen, we just hoped it wouldn't. We hadn't gotten around to fixing it yet. So for example, we saw one team that just indirectly called winexec, which is a DLL export, so it's a valid indirect call target. And they called it with controlled parameters, and they launched some executable off of a network share. We also saw some people that were leaking stack addresses and then using those stack addresses to call nt-continue. Now you might be wondering, wait, why is somebody leaking a stack address and then calling nt-continue? And it's because I didn't tell you something. When we found these classes of dangerous functions like nt-continue, we put a little bit of a mitigation in place. We required that before nt-continue will set all of your register state, it verifies that the stack pointers that you're giving it to set are actually within the bounds of your current thread's stack. And our thinking there was, if you know where the stack is, then control flow guard is bypassed. So this is just a nice way of us making sure that you at least know where the stack is before you can control the instruction pointer from NT continue. But that's what people did. They leaked the stack and then they called NT continue. And we also saw one case where someone found a pointer in one of the flash binaries that pointed to some read-write-execute memory. Yeah, it was actually Nico who's sitting here. And yeah, so he just wrote his payload directly into that read-write-execute memory and had a great time. So that was kind of a disappointing one for us. It's like, oh man, you know, we put all this work into control flow guard and then there's just read-write-execute memory laying around. Exploits in the wild are something that I wanted to talk about, but I honestly just don't have time. The good news is, though, that we haven't actually seen anything all that interesting in exploits in the wild over the past 3 years with regards to bypass and control flow guard that we didn't also see in either Pwn2Own or just in our own internal research. So we're not really missing out on much. And then internally, we actually did quite a bit of work on control flow guard ourselves. One of the things we did was we did some internal prototyping on what we were calling Control Flow Guard Plus. Now, as I mentioned before, Control Flow Guard is coarse-grained, and we wanted to investigate if it was possible to make it finer-grained. It's actually something we had considered during the initial design of Control Flow Guard, but we just didn't have the time and resources to fully investigate the idea back then. Unfortunately, what we ended up finding was that there were a lot of compat issues on Windows, and the best granularity that we could get with control flow guard was ensuring that the function you're calling has the correct number of arguments, but we couldn't ensure that the arguments were of the correct type or that the return values of the correct type. And so given that we weren't really getting that much more granularity and the fact that there was going to be probably some performance cost here and there was going to be a lot of developer cost, we figured it's just not worth it right now. This is not the right thing to invest in. Internally, we also were looking for weaknesses in control flow guard, and our red team found something that I thought was pretty clever. They called it their stack spray attack. And what they realized was that the Windows Memory Manager uses the exact same allocator to allocate stacks for a process as it does when a process calls virtual alloc to get some virtual memory. And in JavaScript, if you allocate a really big array, that will end up turning into a virtual alloc allocation. And so what they were able to do was they sprayed some really big stacks that were the size of a heap, or the size of, they sprayed some very big JavaScript arrays that were the size of a stack on Windows. And then they would freeze some of those JavaScript arrays, and then they would do something like create web workers that would cause new threads to be created, which means new stacks to be allocated. And those stacks would be allocated in the exact same virtual address where they had just freed JavaScript arrays. So if you have a use after free in a JavaScript array, then this gives you a super convenient way to just directly start writing to the stack. So I thought that was pretty clever. We also realized that one possible oversight we made with our image load restrictions pillar was that Microsoft ships a number of DLLs that contain scripting engines like VBScript and PowerShell. And it's possible, those are all signed by Microsoft, and it's possible to load those directly into the Edge browser, for example, or the Internet Explorer browser. And so even if we had really good control flow integrity, an attacker could just load PowerShell script in the process and use that to interop with all the system calls and whatnot. So we realized, okay, so we're probably going to need to do something about people just loading script engines. All right, so what did we end up doing about this stuff? Now, whenever we make changes to our exploit mitigations, we kind of categorize them in two ways. We have strategic changes, which we really think about as a change that is robust or contributes to a mitigation being more robust, and we think is like the right long-term direction. And then we have tactical changes, which are things that we know are weak, we know they're fragile, but they're pretty low cost for us to implement, and it will disrupt the way that people are writing exploits, so we just go ahead and do it. On the strategic side, in July, that's when the first version of Windows 10 shipped. And with that, we got the Edge browser. And that was really great for the security teams because the Edge browser has a way better sandbox, and it also gets rid of a lot of the app compat issues that IE had. So that means in the future we can be way more aggressive with exploit mitigations. Then we made a number of tactical changes. One of the things we did was something that we called explicit suppression. So we realized, hey, attackers are calling winexec and ntcontinue because these functions are valid indirect call targets. And we don't think that anyone should ever actually be calling these things indirectly. So we're just going to go and mark those as invalid call targets. We also spent some time trying to find areas where stack addresses were being leaked onto the heap or into global variables, because that was another thing that we had seen at Pwn2Own. But we quickly realized that there was no way we were going to be able to find all of these, and it's just, like, some of the cases were really easy to fix, and some of them were actually really quite complicated to fix, and we decided this is not the right place to spend our time. And then one continuing theme through all Windows releases is just fixing instrumentation gaps. These are areas where control flow guard was not properly added to a binary, and so there are indirect calls that are not instrumented. And then later in 2015, because with Windows 10 we now ship multiple Windows releases per year, we made some more changes. So this is where we first started implementing our image load restrictions pillar of our strategy. And what we did here was, one, Edge will now only load binaries that are signed by Microsoft. And two, Edge will not load any binaries that come from a network share. And both of these are enforced by the kernel. We also made a few more tactical changes. One thing we did was for Edge specifically, we gave it even more functions to explicitly suppress. These are functions that we weren't really comfortable doing system-wide, but with Edge we could be a little bit more aggressive. And we also did stack isolation, which in response to our red team stack spraying attack, what we did was we gave the memory manager a new allocator that it uses just to allocate the stacks, the TEBs, and the PEBs. And so that guarantees that you can never have like a virtually allocated region of memory that's right next to or on top of a stack. And then one other thing that we realized was that now that we have this explicit suppression thing in place, we have this issue, which is that there could be dangerous wrapper functions. So if you, for example, explicitly suppress winexec from being called indirectly, then what happens if there's a function called winexec wrapper that is a valid indirect call target and then just passes its parameters to the real winexec function? That just immediately bypasses all the explicit suppression work that you've tried to do. So we went and found some of these things using static analysis, but this was another area where we very quickly realized that we were just not going to be able to find all of these. And I'll talk a little bit more about this in a little bit. So 2016, new year, new set of learnings. We actually learned a ton of stuff about control flow guard this year. First up was Pwn2Own, and also we had PwnFest in 2016. That happened in November, so these like the chronological ordering of the slides gets a little bit funky. But the point being that at all of these exploit competitions, we saw the exact same thing being used. People were just leaking the stack address, directly corrupting return pointers that were stored on the stack. They were using that to create a little ROP payload that would create some read-write execute memory for them, and that's where they deliver their second stage payload. And that was ubiquitous. And we had lots of bounty reports in 2016. One of the really interesting bounty reports we got was attacks against read-only memory. Now, I kind of skimmed over this when I was talking about how control flow guard works, but I mentioned how control flow guard has this check function that checks the bitmap to see if something is a valid indirect call target. The way this actually works is there's a function pointer that stores either the address to this check function or it stores a no-op function. And the reason that we do this is because for functions that don't support control flow guard, we need an easy way to disable it. So when a process doesn't support control flow guard, this icall function pointer, it points to the no-op. It just always says, yes, this function you're trying to call is a valid indirect call target. And what people realized they could do was they could make that memory writable, and they could change that CFG check function pointer to point to the no-op function. And now all of a sudden, every single call target in the process is a valid indirect call target. We also saw people that were similarly making memory read-write execute. So even though functions like virtual protect were explicitly suppressed, they found wrappers around these and would make memory read-write executable. And there's also an interesting case for our JITs. At this point in time, our JITs were still in process, and the way that the JITs work is they would JIT some code to read-write memory, and then they would flip the memory protection on that code they just JITted and make it read execute. And we figured this is a pretty small window. We don't think that somebody would be able to write their own malicious code into that JIT buffer before it got made read execute. And it turns out that we were wrong. People were able to do that. We also had some interesting compiler bugs. So we noticed that some DLLs were being generated with writable import address tables, which is a really big problem because all of those function pointers in there get called, they don't have any CFG check happening on them. They are just trusted function pointers. So if someone can modify them, then you can, by design, make those IAT entries point anywhere you want. There was also a case where the compiler was generating some thunks for just internal purposes, and these thunks would take in a function pointer from the RAX register and call it indirectly without any sort of CFG check. And it wasn't actually an issue because there was no possible way that an attacker would ever be able to influence the function pointer that was passed in, except that the compiler was accidentally making all of these thunks valid indirect call targets, which meant that actually you could easily control the RAX register value that was being passed in there. So that was a direct control flow guard bypass as well. And then we saw kind of more of the same. We saw more data-only corruption attacks, people finding interesting DLL paths stored in the heap or in global variables that they could corrupt. We saw people reporting us interesting ways they could leak stack addresses, uninstrumented indirect calls and binaries, and we saw some interesting research on really testing the limits of coarse-grained CFI. And I have a pretty good link to an article that really explores that at the end of the slides. So one of the things that we realized, and I kind of hinted at this earlier, was that no matter how fine-grained our control flow solution is, we end up with this predicament where attackers can still probably call any function they want in your program with arguments that they control. They can either do this because they'll find some wrapper around that function that's a valid indirect call target, or they'll do this because the arguments that get passed to that function are stored on the heap somewhere, or are stored in a global somewhere, or are stored on the stack somewhere, and they can overwrite all of that because they have an arbitrary read-write primitive. And it's probably not the case that it's trivial for attackers to call any function that's loaded in your program with controlled arguments, but from our perspective, we have no good way of reasoning about which functions an attacker can actually call with controlled arguments and which functions they can't, which means that we just have to assume that they can call all of the functions with valid arguments. So in this world, we are still killing ROP because we can guarantee that an attacker cannot call into the middle of a function, but we have to assume that a particular process is going to be able to do or exercise any functionality that it actually has access to exercise. And for us, this means that control flow integrity really has to go hand in hand with a super strong sandbox. So the sandbox is there to limit what a process is able to legitimately do. And we have some of those restrictions in place already, right? So we say you can't load images off a network share. You can't load images that aren't signed by Microsoft. And then control flow integrity's responsibility here is to make it really, really annoying for an attacker to try to exercise any of that program's functionality to escape the sandbox. So in our minds, the two really go hand in hand. One other attack that we realized we had to deal with were binary downgrade attacks. And we realized this after we saw these compiler bugs coming through, because we ended up having to recompile these binaries, but all of the old binaries are still out there. They're still published. They're still signed by Microsoft, which means that they can still be loaded by Edge. If someone writes that binary to disk, which we assume they can do, because as I just said, we assume that that process can do any functionality that it has permission to do, and Edge certainly has permission to write files to the temp folder, then we assume an attacker can drop an old version of a binary that is still signed by us to disk and load it. So we realized, yeah, okay, we really need some way of better controlling what binaries are being loaded. We can't just say you need to be Microsoft signed. And then one other really cool attack that we figured out, and this was actually as part of the effort with Intel to build CET, which was both forward edge but also, more importantly for us, backward edge protection, is what we call a code replacement attack. So if you look at this diagram here, I have this super short call stack. There's a DLL called foo.dll, and it has a function called startWork. And that function calls into a second DLL, and it calls the doWork function. Now, what happens if an attacker, while that doWork function is sitting there in a loop doing some processing, an attacker forces that process to unload foo.dll? And then an attacker forces that process to load a new DLL called bar.dll at the exact same virtual address that foo used to be loaded. And of course, bar.dll is signed by Microsoft. It's a completely valid binary. Well, when that doWork function finally returns, even with CET in place, CET will verify you are indeed returning to the correct virtual address that is saved on the shadow stack. Except that that virtual address is really not what anyone was expecting. It's now potentially the start of a ROP payload. And so we realized, yeah, we need to do some work to prevent this sort of attack from happening. We can't just let people unload code pages at any arbitrary point in time. All right, so we got about halfway through 2016, I'd say, and what we decided was we have a big problem. Everyone is just attacking the stack right now, and even though we have a growing list of design-level issues that we need to find ways to mitigate in Control Flow Guard, mitigating those issues is actually going to have very little value add right now because nobody is bypassing Control Flow Guard by attacking Control Flow Guard. They're bypassing Control Flow Guard by corrupting return pointers on the stack. And we'd really prefer not to wait for CET because even if CET shipped tomorrow, it's going to take many years before it has full market penetration. And so from our perspective, that means our customers are still at risk. And that is when someone on our red team, Jordan Rabet, had a really awesome observation. He noticed that on Windows, the FS segment register is not used by user mode at all. It's a completely unused register. And that allowed us to do something what we thought was really cool. We create a 1 terabyte region of virtual address space in user mode. And we make this region completely opaque to user mode. So if user mode tries to query this region using virtual query, they receive no information about what is mapped in this region, what is unmapped in this region. It's just a big blob to them. And any access violations in this region are fatal. Even if you're inside of an exception handler, if you blow up inside of this region, the process crashes. And then what we can do is we can allocate shadow stacks at random positions in this region. And we can point the FS segment register to the shadow stack of your particular thread. And then what we do is we use our compiler to modify all the code. And in the prologue of every function, we emit 2 instructions that simply move the return pointer for your function onto the shadow stack. And in the epilogue of the function, we retrieve that stored return pointer from the shadow stack and check to see if it's the same as the return pointer that's currently stored on the normal stack. If it isn't, then we blow up the process. And if it is the same, then we allow you to return. Now, there's 2 really important things to realize here. The first thing is this relies on a secret, which is something that Control Flow Guard had hoped to avoid. The secret is the location of that shadow stack. If someone knows where it is, then they can go and corrupt the values on it. The other thing to realize is that there are two by design race conditions here. If an attacker is able to corrupt the return pointer on the normal stack before it is copied off onto the shadow stack, then return flow guard will be bypassed because that corrupted return pointer will be used in the epilogue check. And similarly, in the epilogue, if the attacker is able to corrupt the return pointer on the normal stack after the epilogue check runs, but before that return instruction executes, then they can also bypass return flow guard. So we did all this development, and then this ANC attack was published. And this is a hardware timing attack that allows you from JavaScript in the web browser to determine if any particular virtual address is mapped or not. And because this doesn't rely on directly accessing the memory, it's a microarchitecture timing attack that looks to see what pages in the page table are mapped. It means that they can actually successfully de-anonymize the shadow stack region, and they can figure out where all the shadow stack pages are mapped. Now, the POC that we built in Edge for this to test RFG, it took several minutes to run. But one thing that we know about attacks is that they usually don't get worse over time, they usually get better over time. So while it took us a few minutes, give someone a couple more years, it might take a few seconds. But the real nail in RFG's coffin was actually the race condition. So when we originally were thinking about this race condition that RFG had, we figured it's probably going to be pretty impossible to win this race with any sort of reliability, because if you attempt to win the race, we think you're either going to you're going to try to corrupt the return pointer a little bit too late. You're going to do it after the epilogue code has run. And if you do that, then the prologue code is, I mixed that up. You're going to do your write after the prologue code has run. And then the epilogue code, which checks right before you return, is going to blow up. Or you're going to do your corruption attempt at a completely incorrect time, and you're just going to corrupt some random piece of data on the stack frame of another function. And maybe that'll cause the program to crash, maybe it won't, but in either case, it won't result in RFG being defeated because you won't have successfully corrupted a return pointer. But we had someone named Reed Borsuk who was on our red team, and he was taking a look at RFG and he was trying to figure out, how can I win this race? And Reed realized he has two important things right now. One, he knows where the return pointer is going to be stored on the normal stack, because per our threat model, the attacker has arbitrary read-write and they have full knowledge of the address space of the process. And Reed also knows that he has control over at least two threads in a process. In Edge, you have the ability to spawn web workers, and it's possible through data corruption that you can end up bending the control flow of any of those threads and getting them to do somewhat arbitrary actions. But what Reed needed is two things, really. The first thing he needs is, when he attempts to win this race, when he attempts to corrupt the return pointer, he needs the process to not blow up if he fails to win his race. The second thing he needs is he needs to actually be able to win the race sometimes. And all of this kind of comes together with this realization that if you look at this histogram that Reed created, we have what we call thread 1. And thread 1 spends the vast majority of its time inside of a sleep function. And that sleep function does absolutely nothing. And every once in a while, that thread will wake up and it will call getLength, and getLength will call stringLength. And he decides he is going to target the return pointer of that stringLength function. Now, if you look at the stack depth over time, you can see that at the virtual address that return pointer is stored, the vast majority of the time, that memory isn't being used by anything, because the sleep function stack frame is much higher. It's not going to be corrupted. And that means that if you perform a write to that virtual address at any given point in time, on average, you're going to be corrupting nothing. Now that's very good, because that means that his first condition is satisfied. Failures to win the race do not actually crash the process. And what this allows him to do is he can create a second thread. And that second thread just enters a very tight loop. And all that that loop does is it attempts to write a corrupted return pointer to that virtual address where the legitimate return pointer is stored. Now, when he starts that loop, on average, you're going to be in the sleep function on the first thread, meaning that that loop is going to be corrupting nothing. However, when the getLength function is called, and it goes and calls the string length function, that loop is still running. And that loop actually has effectively a 100% probability that it will overwrite that return pointer after the call instruction is made, but before that prologue code can safely store the return pointer to the shadow stack. And so I think in Reed's POC that he made, he did 5,000 attempts, and I don't think he saw a single failure. And then we worked and built a POC inside of the Edge browser, and that POC, I think, was also 100% reliable. So with control flow guard in place, with return flow guard in place, we were able to hijack control flow by exploiting this race condition with basically 100% probability. And this was a little bit unfortunate for us, to say the least. So we spent some time looking at this and trying to think, is there a way that we can fix RFG to make it resistant to this race condition? And we came up with a few proposals, but those proposals either would hurt performance quite a bit, or they would really blow up the size of the binary because we'd need to add lots more code to the prologue and epilogue, or potentially to the function callers. And neither of those was acceptable for shipping the mitigation. And so it ended up being killed. Now, while we were going through this, we realized a few things. Techniques exist to extend race condition windows. One way is if you have a race condition that crosses cache line boundaries, and so some of the code is paged out, then that naturally extends the race window for you because the CPU will have to go and spend time loading in code to finish its execution. Another way that you can make races even easier to win is you can call system calls like suspend thread and get thread context. So you can actually suspend another thread, and then you can retrieve its register state, and you can look at the instruction pointer and see, am I at the right place to start executing my race, my race condition or not? We also realized that more races exist in our existing CFI strategy. So the unwinder in Windows, which is used for handling exceptions, among other things, has a number of places where it will go and it will set CPU register state. And this is actually one of the places where ntcontinue is called. Now we have checks in place in ntcontinue to say, oh, you can only set the instruction pointer if you know where the stacks are. But that's all vulnerable to racing. And the CFG check function itself actually has a race condition built into it in combination with code replacement attacks. If you can suspend a thread right after the CFG check function is made, and then unload the DLL that you were about to indirectly call into, and load a new DLL in its place, then you're going to indirectly call into who knows what, whatever the attacker chooses. But at that point, the CFG check function has already executed. So what we realized here is that for CFI to be robust against targets that we really care about, like web browsers, it is not sufficient to threat model against an arbitrary read-write primitive. You must threat model against an arbitrary read-write at arbitrary times primitive. So all race conditions are fair game. And it's worth noting that today there is no CFI solution that is robust against this sort of threat model. And I don't think that aside from CFG, there's any CFI solutions that are attempting to be robust against this threat model. But I could be wrong about that. Okay, so that was a huge information dump. We're going to pull out our problems we found, talk a little bit about some changes we've made now. In 2016, this was sort of as RFG work was in development. We continued to make some improvements to control flow guard. One of the image load restrictions, or a mitigation that falls into the image load restrictions pillar, was enabling no child process for Edge. So this makes it so that Edge can never spawn child processes. And we also made some tactical changes. We hardened the long jump call a little bit, but it's still not robust. All right, so in 2017, we didn't really do quite so much research into CFI. At Pwn to Own, we continued to see the same trend. Attackers were going after the stack, they were creating read-write-execute memory, and they were delivering their payload that way. And on the bounty, most of the cases that we were receiving revolved around binaries that were missing instrumentation. But we did receive a few interesting bugs in arbitrary code generation, which I'm going to talk about here in a second. Arbitrary code generation is our dynamic code restriction pillar. So this prevents a process from allocating new executable memory. And so with this change in place, it should no longer be possible for attackers to use a ROP payload to virtual protect read-write-execute memory. We also enabled the no mandatory low label images mitigation for Edge. That's a very long mitigation name. What that means is when Edge writes a file to disk, because Edge is sandboxed, that file will have a low mandatory label on it, and there's no way for Edge to remove that. And all that this mitigation does is it prevents Edge from ever loading a DLL or EXE that has a low mandatory label. This is intended to stop downgrade attacks. You can't write an old version of a Microsoft signed binary to disk and then load it. And we also enabled support for CFG strict mode in Windows. So it is now possible for a process to say, I only want images loaded that support control flow guard. All right, so after all of this work, this is, well over 5 years of effort and over 3 years of having control flow guard actually enabled in Windows and shipping. Where are we now? Well, we do have control flow guard. It is shipping. It does have a few design level problems right now, but it's there. Split stacks, we still aren't there yet. Image load restrictions, we've made pretty good progress. There's just one thing really left to be done that I'll talk about in a second, but we do have code integrity, we do have no child process, you cannot load images that have a mandatory low label, and you can't load images over the network. So effectively, you can only load Microsoft signed images that are already installed on the system by a higher privileged user. And on the dynamic code restrictions pillar, we do have arbitrary code guard enabled, and it is working as we intend it to. There have been some bugs, but the design has held up. So what is left to do? And I realize this text is very small because there are a number of things left to do. For Code Integrity Guard, the main thing that we need to do is we need to have a way to be more granular with what binaries we allow to be loaded into a process. So even though only Microsoft signed binaries that were already on the system can be loaded in Edge right now, we really need to stop things like scripting engines from being loaded in. For Arbitrary Code Guard, we think it's working as intended, minus the bugs that people have found. For CET, well, we need hardware to be released. And for Control Flow Guard, we have a number of things we need to do. To mitigate these code replacement attacks, we really need to prevent sandbox processes from being able to unmap executable code pages unless a broker says it's okay. And presumably the broker would need to go through the call stacks of all the threads to make sure that none of those threads have a call stack that's going to return into that code page you're unmapping. Similarly, for these read-only memory attacks that we have, we also need to have a broker that decides if a process is allowed to unmap or change the memory protection of a read-only memory page. And it would probably just be for specific protected read-only memory pages. Race conditions is kind of an open-ended question. We know that we probably need to move the entire unwinder out of the process. And we think that the CFG check race condition that I talked about will be killed by code replacement attacks being mitigated. All stack-related issues we think will be addressed by CET. And coarse-grained CFI limitations are something that we're going to continue doing research on finer-grained CFI, but we're not 100% sure what we can do there yet. All right, so what would I like you to take away from this? Well, doing good CFI is really hard. It is not an easy solution. There's lots of performance penalties involved, lots of engineering effort involved. But for this thing to be robust, it really needs to be threat modeled against arbitrary read-write at arbitrary times. Nobody actually is robust against this right now, but we're trying to be. And we think that we have line of sight to get there. Another point is to maximize the benefit you get with CFI, it needs to be combined with strong sandboxing. The two have to go hand in hand. And from our observations, even though we currently have a CFI solution that is not robust, we do still see this increasing the complexity of exploits that are being written, and particularly things like arbitrary code guard we think are going to cause people a lot of pain because it's going to force payloads to be delivered entirely in ROP. So we think that there's still value even if it's not perfect. And the last thing I'll mention is that Microsoft does have a number of bounties, and a number of these things were actually found thanks to the mitigation bypass bounty. So if you guys want to participate, we would love to have you participate. Thanks.
Any questions? How do you protect against doing things like messing with the bitmap or messing with the pointer from the PEP to the bitmap?
So the bitmap is protected by the kernel. It cannot be made writable by user mode. And protecting the pointer to the bitmap, I don't think the CFG check function actually follows the, I don't think it follows a pointer from the PEB. But if it does, that's just another case of pointers that we need to ensure actually stay read-only. So it falls into that bucket of read-only memory attacks where we need to have some better way of protecting certain sensitive pointers.
Okay, so split the PEP into a variable and a constant part?
Yeah, presumably.
Okay, so two things. So regarding the ANC attack that you mentioned, as far as I can remember, that only permits them to leak a part of the address because they can only determine the cache lines that are used inside the page tables, but not exactly which page table entries are used. So did you investigate whether it would be possible to rely on a small amount of randomization that would be inside cache lines, or would that break because of these new side channel attacks that rely on store to load forwarding or so?
Yeah, so I don't think that we spent a whole lot of time investigating how to mitigate that because very shortly after we were successful in exploiting this race condition, which was just there was no way that we could mitigate it. I know that we did do some thinking about if there were ways we could mitigate ANC, but it starts to get into really scary territory because people are just finding, as you know, more and more hardware side channels. And so when that ANC attack was discovered, it really sort of solidified to us, we're taking a big risk by trying to depend on hiding secrets. But really the timing attack was the nail in the coffin, and we just stopped looking at how to protect against ANC after that.
So regarding the timing attack, I'm wondering why you did not mention the possibility of trying to pivot the stack pointer to the control stack, then doing the call or return instruction on the other stack, and then pivoting the stack pointer back. Is that just for performance reasons, or?
Yeah, so we did some preliminary benchmarking on that. So the idea is that if instead of returning from the stack pointer, you transition your stack to be the shadow stack and then you return, I think there's a few issues there. One, we need to be very careful about, since the stack pointer now actually points to the shadow stack, then someone can call get thread context and now learn where the shadow stack is located. So we need to be very careful there. And it also did seem to cause performance issues on Intel modifying where you were returning from at all, like the stack you were using. One thing we considered was switching from returns to jumps that just jumped directly from the shadow stack. That also caused really big performance penalties because now you're not using the RSB, the return buffer. And so that was like a multi-point performance hit. So yeah, it basically came down to those two things. One, we now we're at much higher risk of leaking where the shadow stack is, and two, it was hurting performance.
Okay, thanks.
Yep.
Any more questions? I have a last question, if nobody else has a question. Yeah, my question is, I know that the Windows security team is doing great work with so much of research as well as the bounty. Why does Windows 10 still ship with baked-in Adobe Flash, which is not removable by end user? So we know that there are Adobe Flash 0 days out there, and they are exploited every now and then. Why does Windows 10 still ship with it? It's baked in, it's so deep in that even takes me, for example, with my script or with my expertise with 15 years of research with Windows, it takes some time to remove it, right? Why do you still ship it with baked in Adobe Flash?
I do not have the answer to that question. Sorry.